Okay, the next section we're going to talk about is what is the sun's energy source. This is to say that the sun is shining, it's producing energy all the time. What is it that allows it to produce that energy? And we're going to look at this to start with a historical perspective. So there were a couple of different ideas that were put forward before we came up with what is now known to be the correct source of energy. So it's the idea of chemical burning. So basically, if you've got hydrogen and oxygen, you stick them together, you get an explosion. And this is basically what rocket fuel is. And so one of the original ideas was that the entire mass of the sun was made of hydrogen and oxygen, and as they came together you would get this energy released. Turns out that that doesn't last very long. It's a few thousand years, and so since we know what the mass of the sun is, we can work out how many reactions we have, and so that wasn't very satisfactory. The next idea was that you have gravitational collapse. So you have the system is made of distribution of hydrogen particles, and as they collapse down, they're converting potential energy to kinetic energy, and that is then released as radiation. That actually lasts a little longer. It's called the Kelvin-Helmholtz time, and that can last about 20 million years. It's a lot longer than people thought we needed until we started to date the solar system, so it actually stuck around for quite a long time. It turns out that that's probably the timescale for the collapse of the nebula until the sun actually starts fusion. But in fact, we now know that nuclear fusion is the main source of energy for the sun. And in the case of the sun, it is taking hydrogen and fusing hydrogen nuclei to make helium nuclei. But how does this produce energy? In what way does hydrogen fusion give rise to energy? Well, the simple answer is that when you take 4 hydrogens and you stick them together, you convert 2 of them to neutrons for a start, but the mass of the helium is smaller. And so we use what is probably the most famous equation ever, E equals mc squared, and the missing mass is the m, and that gives you the energy. And this is basically considered to be binding energy. That is to say that if you wanted to break helium apart into its component pieces, you would have to provide this energy back to break up the nucleus. And so in fusion, this is the energy that is made by sticking hydrogens together to make helium. And so we're going to go through this in a little bit of detail. And so, you know, we all know that we have atoms. They're made of protons and neutrons. So if you've got helium, it's just a proton. Or actually we have isotopes. So we've got hydrogen, which has 1 proton in. You can have deuterium, which is still an isotope of hydrogen. Still only has 1 proton, but now it has a neutron. And tritium, which is very rare, has 2 neutrons. And then depending on the number of protons, you have different elements. And so here we have hydrogen, which has 1 proton, helium has 2 protons, lithium has 3 protons, and so on. And so how all of these come together, we'll get into a little bit of detail. So what really matters is, what is the binding energy? That is to say that you're sticking together these hydrogens. For every hydrogen, you lose a little bit of mass on sticking them together, and that's what gives you the energy that's released, and that is called the binding energy per nucleon, where nucleon just means protons and neutrons. It's a catch-all term for particles in the nucleus. And so the binding energy per nucleon is basically the difference between the mass of the atom and the mass of the number of hydrogen atoms it would take to make it. So as an example here, I've got oxygen 16. The binding energy per nucleon is, it would take 16 hydrogens, half of which would turn into neutrons. And if we multiply that mass of hydrogen by 16 and subtract off the mass and then divide by 16, because it's per nucleon, we get the binding energy per nucleon. And it turns out that actually the biggest change in binding energy is, so here we have hydrogen, and then we've got helium has a high binding energy per nucleon and so on. But as you make these bigger and bigger elements, you get more and more binding energy until you get down to iron. Once you get to iron, that is the most stable. That is to say, it will take the most energy to break it up. And so actually elements that are bigger than this particular isotope of iron will actually get more stable by falling apart, and that's where fission comes in. And so by fusion you can make elements up to iron. You can't make elements past iron, and we may or may not come back to that later. like I say, here they still have some binding energy, but now they can get more stable by falling apart. So, to summarize that idea, the higher the binding energy, the more stable the atom is, and so as you stick things together you get more and more stable until you get to iron 56, which has 30 neutrons and 26 protons, and this has the highest binding energy of any element or isotope. And so for elements that are smaller, less massive, you stick them together, you get something more stable. For things that are more massive, then they will split to become more stable. So let's go back to the fusion in the Sun. Fusion doesn't happen all the way through the Sun, it only happens in the core. Well, the question is why? Why doesn't it happen everywhere? Well, there are some barriers to getting hydrogen nuclei to stick together. So if you want them to stick together, you have to get them to essentially collide. They have to come close together. But that's a problem because a hydrogen nucleus is a positive charge. And so if you want to bring two of them together, then you've got two positive charges. Here this is for any nucleus. So if it's a proton, then it has the same charge as an electron, so it just says E. The Z gives you it for any element. And so it means that you have a Coulomb repulsion that is, this K is the 1 over 4 pi epsilon naught. This is the Coulomb repulsion. So you've got the atomic numbers, the charge on an electron, and the distance between them. So as you get them closer, the force between them gets stronger. And so what we have is that we need to get them close together, and that's only going to happen where you have very high densities and temperatures. So essentially what you've got is that as you bring the particles together, they will get pushed apart more and more strongly, more and more strongly, more and more strongly, until they're really strongly pulled. Once you get them past that point, they fall into a well and they can be attracted, and this is the strong force. And so mostly the positive charges will keep themselves apart, but if you can get them really close together, then you can cause them to overcome that. And so you really need high temperatures of the order of 10 to the 7 Kelvin for hydrogen. And this is so that you have the velocities or energies required to overcome that electrostatic repulsion. And so you need really high densities so that you have lots of collisions, and you need really high temperatures so that you can overcome the repulsion. So here I have an animation that I'm going to show you. So here we have two hydrogens that come together. One of them converts to a neutron and it emits a positron, which comes along with an electron and gets annihilated and releases some energy. Another proton comes along, that's another hydrogen, and now we've got a helium, but it's not the most common isotope. And now another one of those comes along and it ejects two more protons, and we end up with helium-4. Let me show that again just to make sure that we get it. So, two hydrogens come together, one becomes a neutron, and see here, it became a neutron, it had to eject a positron to get rid of a positive charge. A positron is an anti-electron. It meets the electron and annihilates, and that releases energy. And so now we have some energy that was released, and now we get another proton comes along and more energy is released because it's bound, releases some energy, and now this comes along and rearranges itself. And so that's the basic process. This is kind of showing it in a static form. So I've got two hydrogens, they come together, ejects a positron and makes a deuterium. And then another hydrogen comes along, makes a helium-3, and then another one of those comes along, made by the same process, and that makes the 4. And so it takes several steps, and this proton-proton process, so proton-proton being you need two protons to start it, this is very common. There are actually two basic processes, so it's called the proton-proton chain, and there are some additions to it that you can make. And this is very common in stars like the Sun, where the temperature is less than about 20 million Kelvin. There's also this CNO cycle, and the CNO cycle is really interesting, and we'll get into this in a second. And for some stars that are a little more massive, where they have high temperatures in their cores, this can really dominate. It actually causes more energy release. So the Sun, it's the proton-proton chains, but in more massive stars, it's the CNO cycle. You have both going on in the Sun, but the proton-proton chain is more common. But basically, this works by having carbon as so here I have a carbon-12. If I add a hydrogen, I get a nitrogen-13. Nitrogen-13 isn't stable. It will eject a positron and make a carbon-13. Carbon-13 is stable. You add another hydrogen and you get nitrogen-14. Nitrogen-14 is stable. You add another hydrogen, you get oxygen-15. That is unstable, releases a positron, makes a nitrogen-15. That then is stable, gets another hydrogen, and at this point you can make an oxygen-16, but it's more likely that you're going to make a helium come off and be back with that carbon-12. So basically you start with a carbon-12, you end with a carbon-12. You take 4 hydrogens, you stick them together, and you make a helium. So it's doing the same process, but now it uses the carbon as a catalyst. And so that can be important. But this is something that really needs higher temperatures to become dominant. And it has to do with the fact that you're not just using hydrogen and helium, you're using other elements. And so these Z's for the Coulomb repulsion become important. So the Coulomb repulsion is proportional to Z1, Z2. For the pp chain, you've got add a hydrogen to hydrogen and a helium to a helium. So the worst case scenario is you have a Z1, Z2 is 2 times 2 is 4. However, if you have carbon and you're adding a hydrogen and you're adding a hydrogen to nitrogen and a hydrogen to oxygen, you have to worry about these atomic numbers, which are 6, 7 and 8, and so the Z1, Z2 ends up being higher, and so your Coulomb repulsion is higher, and so you need a higher temperature to make it happen. We call the process of making new nuclei nucleosynthesis. It just means exactly that, the synthesis of new nuclei. For the Sun right now, it is mostly doing proton-proton chains, and it's only doing hydrogen fusion. In its future, it will make other elements, and we'll maybe talk about that when we do stars, but for now it's only doing this with hydrogen and making helium. So, nuclear fusion only happens in the core. The high temperatures are needed to overcome the Coulomb repulsion. Only about 10% of the Sun's mass is available as fuel, because that's the only material that is at high enough temperatures and pressures or densities. And only hydrogen atoms are fuel, although it's mostly hydrogen anyway. So we can do a rough calculation to work out how long it'll take for the Sun to use up all of its hydrogen. In order to do this, we need to know how much fuel we've got. So that is, how many hydrogen atoms have we got, and then what do we get for each of those fuel cells. So for each hydrogen atom, how much energy is released. So let's go through this. We have a solar mass, right? We have solar luminosity, so we know the rate at which it is releasing energy, and if it isn't producing energy at the rate it's releasing it, it will not be in hydrostatic equilibrium. And so that must be happening. Only 10% of the mass of the core is in the core, so we can divide this by 10, but we also know that it's only about 75% by mass is hydrogen. So we don't have 2 times 10 to the 30, we have more like 1.4 times 10 to the 29 kilograms available. Now, we know that a single hydrogen atom has a mass of this in AMU. This is atomic mass units, and so we can convert this into kilograms. And so since we know how much mass we've got, and we know what the mass of one unit is, we can work out, by dividing one by the other, how many hydrogen atoms we've got available to us. This is an oversimplification, because some of this mass is, oh no, that's fine. It is an oversimplification, but I'll come back to that. So, now we need to know how much energy is released. So here I've got the mass of a hydrogen and the mass of helium. What I need is the difference. So 4 hydrogens is 4 times this, a helium is this. The difference is a fraction of an AMU. And so the mass lost per hydrogen is this divided by 4, because this is for 4 hydrogens. And so we're losing a very small fraction of the mass. We know what an AMU is in kilograms, so we can convert this into, this is the number of kilograms that are converted We know that E equals mc squared. We've got the mass. We know what C is. So we can simply work out that for each one of these hydrogens that is used, we get about 10 to the minus 12 joules. So we have, each one makes 10 to the minus 12 joules. We have about 10 to the 56-ish. And so we multiply one by the other. We know what the total potential energy is. That is, how much energy is totally available if you convert all of those hydrogens to helium. We also know the rate at which it's being used. So now we have the total amount, the rate at which it's being used. We divide one by the other, and we get the time in seconds. That doesn't help as much. It's not very intuitive. So it comes out to 7-8 billion years. And that's where, there is some evidence for nuclear fusion. So we like to know that we have evidence for these things. In this case, it's something called neutrinos. And so you'll notice that we have two hydrogens, they come together, positron disappears, one of them turns into a neutron, but there's also this other particle called a neutrino that is ejected at the same time. It is a fermion, which is the same is true for electrons and protons and neutrons. It's also a lepton, which is also true for electrons. And one of the things about elementary particle physics is that you have to have some balancing of the numbers of different types of particles. It's almost massless, even less mass than an electron. And it does not experience a strong nuclear force. So, whereas the nuclei are stuck and interact with each other and get stuck in the deuterium, we get the neutrino can just escape. And so the neutrinos exist for two reasons. You have to balance the momentum, and you have to balance the number of leptons in a nuclear reaction. So for making a positron, you get a neutrino. If you make an electron, you get an antineutrino. Protons and neutrons are also fermions, but they are hadrons, that is, that they experience the strong nuclear force, whereas the electrons do not. And so we detect neutrinos. It's very hard to detect them because they interact very weakly, but they do interact very occasionally, and so if you can set up an experiment to detect them, then you're in good shape. You can't actually look at the interior of the sun directly, but the neutrinos come, they interact so rarely that most of them escape, and we can predict how many should escape. And so they can actually penetrate, go straight through us, straight through the Earth. And so experiments have been designed where you have a tank of very pure water, and you have the neutrinos going through the water, and very occasionally they will interact and cause a nuclear reaction which will give rise to a flash of light. And so here we've got the original experiment where it's a big tank inside a big cave. But the problem was that there was a prediction as to how many neutrinos we should get, and only about a third as many appeared. Turns out that neutrinos don't stay as just one type of neutrino. They change to different types. And so there are actually 3 different types, or flavors, but the experiment was only designed to detect one type. And so we don't see all of them, we only see the third that are in that particular flavor. And we'll stop there and come back to the solar interior again in